Video is going to serve as kind of a capstone, a very good summary of section 11.3. We're going to work through analysis of functions using calculus with a focus on the first and second derivatives and their applications for the analysis of functions. Now, back in your pre-calc days, you did analysis of functions of polynomials like this, and there were a few things you were able to do. You realized, hey, this polynomial, and this is the one we'll work with, y equals x to the fourth minus 4x cubed plus 4x squared minus 2. You realized a couple things automatically. You knew that this had what? N behavior that was headed towards infinity in both directions because it was a function that was a even degree with a positive leading coefficient. You probably also at some point in time approximated drawing the graph. You might have been able to find a couple real roots on your calculator. You might have also noticed that, gee whiz, you don't have all of the roots on this. You should have 4 roots total here, some of those roots which might repeat. But if you look at just kind of the graph that you would get in the calculator, and this is a good proxy for that graph, you'd see that there's 2 real roots, there's 2 imaginary roots to this particular polynomial. For the purposes of what we're doing today, I'm not really focused on those 2 real roots. I'm more focused on all the other stuff that happens in this polynomial. And this is a good graph. I took it from Desmos. You could put it in your calculator as well. But it's a pretty good graph. I set this problem up so some of the numbers were kind of nice, which will make our algebra in a little bit easy. But with a function like this, you know you're going to have some turning points. And gee whiz, when you have turning points, you typically might have relative max, or relative mins, absolute mins. In this case, you notice some turning points, which is very useful. And we're going to use calculus, not our calculator, to identify the coordinates of these points. There's something also that you might have noticed as you look at this when we start talking about the concept of concavity. For a long portion, as I'm following with my pen, probably up to about here, so all the way over here up to about there, this is a concave up function. Somewhere it becomes concave down. Somewhere before it makes this turn, before it gets to this little, hey, by the way, that's a local max. Somewhere around here maybe is where we see a concavity change. We go from concave up to concave down. And by the way, the same thing kind of happens somewhere around here. We're concave down in this little interval between my 2 red dots. And then we change back to concave up. We have a couple inflection points, it would seem, in this graph. So we're going to use the purposes of calculus, or the principles of calculus, to identify these points more precisely. Back in the pre-calc days, you just kind of drew a curve. You kind of knew some max mins, maybe some turning point locations, but you just kind of arbitrarily decided where you wanted to turn. We're going to now precisely identify some of these pieces. And so here's how we're going to work the analysis. For this graph, I'm going to ask you to identify increasing, decreasing, and also max min possibilities. And you're going to do that by working with the first derivative, f prime of x. We're also going to do a little bit of work after we've identified possible max and mins using a sign chart. We're going to use the second derivative test on a couple of our critical points and reconfirm the maxes and mins that we found through the second derivative test. We're then going to do analysis of the second derivative to talk about concavity. When is the function concave up? When is it concave down? When does it have inflection points? Key thing, remember, an inflection point occurs when you go from concave up to concave down, concave up to concave down, or concave down to concave up. Change in concavity about a point means that that point is a point of inflection. And we'll use a sign chart on f double prime, the second derivative of x, to assess that. Now, I've pre-filled a lot of pieces just to save time and not want you to listen to me writing. We've done a couple things over here. I've listed what the 2 derivatives are, so feel free to just go ahead and write them down yourselves. You can calculate them quite easily. F prime of x is 4x cubed minus 12x squared plus 8x. And if I factor out 4x times x squared minus 3x plus 2, I can also factor x squared minus 3x plus 2, wind up with 4x, x minus 2, x minus 1. The second derivative, take the derivative of the derivative. The derivative of 4x cubed minus 12x squared plus 8x is 12x squared minus 24x plus 8. I could take a 4 out, 4 times 3x squared minus 6x plus 2. And we'll talk later, we're going to want to set this to find inflection points. We're going to look where that second derivative is 0. Turns out we're not going to be able to factor that thing cleanly. We're going to use the quadratic formula and then some little bit of calculator rounding to find the exact coordinates where the second derivative is 0, and through a sign chart we're going to see that we're going to identify some inflection points. So let's begin. What I first said was we're going to do analysis with the first derivative. So there's my first derivative one more time, and I've broken it down into the factored form that we talked about. In so doing, I find 3 different values that would set the derivative equal to 0. X could be equal to 0, x could be equal to 2, x could be equal to positive 1. Those are my extreme values, extrema values, critical values. Values of x for which the derivative is equal to 0. I need to figure out the exact location of that point, however. So what am I going to do? Well, for x equals 0, I'm going to evaluate the original function at 0. So my critical point location, the thing I'm going to have to evaluate, is at the point 0, negative 2, because f of 0 is negative 2. Similarly, if I compute the value of f of 2, work my way through the algebra here, you can do this off to the side, I'm going to get negative 2. And if I compute f of 1, I'm going to get a value of negative 1. So 0, negative 2, 2, negative 2, 1, negative 1 are going to become these critical points that I want to assess for max and min. And how do I do that? Through my sign chart. Because I want to get not only max and mins, but I want to talk about increasing and decreasing. So what I've done here is I've taken a sign chart, my different values of x. Notice that at each of these spots where that derivative is equal to 0, I've put a direct entry, x equals 0, x equal 1, x equal 2. And then I've just done all the other x values around that. X greater than 2, x between 1 and 2, x between 0 and 1, x less than 0. And with my sign chart, all I need to do is, hey, put in a value and see what happens to these 3 factored terms. And what I did first in class, but I'll do first here as well, when x is greater than 2, 4x is positive, x minus 2 is positive, x minus 1 is positive. I have 3 numbers multiplied by each other that are all positive. My function is going to be increasing after x is equal to 2. When x is between 1 and 2, 4x is positive. X minus 2 is negative. X minus 1 is positive. I have 2 positives times a negative. I'm going to get a negative number. My function is decreasing between here. And so very quickly, that tells me, gee, when x equals 2, that lovely point 2, negative 2, it's a minimum. I was decreasing on one side. I'm increasing on the other side. I have to have a minimum here. And if we work through the same type of processes, when x is between 0 and 1, positive, negative, negative. X between 0 and 1, 4x is positive. X minus 2 negative, x minus 1 negative. Positive times neg is a positive number. My function, when x is between 0 and 1, is increasing. And x equals 0, I know, hey, what's happened? No problem. Come back and look at these 2 values, increasing on one side, decreasing on the other. I have a relative max at 1, negative 1. Last piece, when x is a negative number, 4x is negative, x minus 2 is negative, x minus 1 is negative. Negative, 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 a negative value. The function is decreasing over that interval, x less than 0. And so again, if you pull up in your calculator, kind of stare at it, you'll see that exact type of behavior. You can see when the graph is decreasing, you can see when it's increasing. What's one more thing that I've realized? I have a minimum, also a relative minimum at 0, negative 2, because I went from what? Decreasing to increasing. So that's the power of a sign chart to analyze the derivative, identify intervals where you're increasing, decreasing, intervals where, hey, your derivative is equal to 0. Remember, when you go from decreasing to increasing to decreasing through a particular point value, you found either a relative min or a relative max. So there's our derivative analysis. That's kind of item number one. Second thing is I said, hey, I want you to go back and I want you to analyze the three critical points and get this max-min concept, not only just by a sign chart, but we'll do something a little bit simpler by focusing on the second derivative at these values. And here's what comes up. When your first derivative is equal to 0, first derivative equal to 0, second derivative positive, you have a max. Excuse me, you have a min. Apologize, let me restate that. When you have a derivative of 0, f prime of x equals 0 for a value of x, and then you compute the second derivative and evaluate it at the same value of x. If it is positive, you have a minimum. If your derivative, first derivative, is equal to 0 at a given value, you evaluate the second derivative at that same given value of x. If the result is negative, you have a relative max. So let's use the second derivative test on our three values. When x is equal to 0, the second derivative, which we said is 12x squared minus 24x plus 8, evaluated at 0, the second derivative is 8. That's a positive number. First derivative 0 when x equals 0. Second derivative equal 8, a positive number when x equals 0. That tells us that that point is a minimum. When x equals 1, first derivative is equal to 0. We saw that up here. Second derivative, evaluate f double prime, the second derivative, f double prime at 1. We come up with a value of -4, which is negative. A negative second derivative, when the first derivative is equal to 0, gives us a maximum. So we're just reconfirming what our sign chart already told us. When x equals 2, derivative, first derivative is equal to 0. The second derivative, f double prime, evaluated at 2, gives us a positive 8. We have another minimum. So, second derivative test here, all we're really using is just kind of confirm our suspicions, also to see the value of the second derivative test, letting us know max or mins. It's a very useful technique and a very useful tool for us. And again, everything that we're seeing here, all the work that we're doing, is summarized in section 11.3. If you focus on the blue text boxes throughout that unit, those are all the key points. If you understand those, you're going to be in very good shape for this unit and for future things that we're going to do in the calculus area. One other thing that I said, just a quick aside, remember, if you stare down the graphs of f equals x squared, f of x equal x squared, f of x equal negative x squared, f of x equals x cubed. If you know what those graphs look like, what they do, understand their shape, understand whether they have a max min, understand their concavity, which you should be able to do with those graphs because they're very, very simple in structure. If you can understand those concepts in blue applied to these three functions, you're way ahead of the rest of the calculus world when it comes to understanding these pieces. You're in very good shape. Okay, the third thing we had to do, if I go back and just kind of show you my graph now one more time, we've really pinpointed where these three green circled points are. We're going to do one more piece of work. We're going to identify the points of inflection, where we go from concave up to concave down, and gee whiz, where we go from concave down to concave up. You can see concavity shifting at this point. You can see concavity shifting at that point. Let's do some work with the second derivative. Now, before, we said what the second derivative was, 3x squared minus 6x plus 2. An inflection point occurs where the second derivative is equal to 0, or a possible inflection point is maybe a better way to describe it, occurs where the second derivative is equal to 0. And again, we're going to do that same type of sign chart as before. I had told you that 3x squared minus 6x plus 2 does not factor correctly. Does not factor easily using any of our techniques. So to find the zeros, to set f double prime of x equals 0, we need to set 3x squared minus 6x plus 2 equal to 0. We're going to use the quadratic formula to find those two root values. 3x squared minus 6x plus 2 into the quadratic formula. Negative negative 6 plus or minus negative 6 squared, 36, minus 4, 3, 2. 4 times 3 times 2 is 24. 36 minus 24 is 12. Over 2a, 2 times 3, 6. So I'm going to have 6 plus or minus the square root of 12 over 6. Square root of 12 is square root of 4, square root of 3, or 2 times the square root of 3. I'm going to be left with 6 plus or minus 2 times the square root of 3 over 6. 6 over 6, first fraction, is 1, plus or minus 2 over the square root of 3 over 2 times the square root of 3 over 6 becomes the square root of 3 over 3. So my second derivative is going to be 0 at the values x equals 1 minus root 3 over 3, which is about 0.425, and x equals 1 plus root 3 over 3, which is right around 1.58. So I kind of rounded. I just did 3 significant digits in both places. All right. I built a sign chart again. I'll let you do a little bit of work. You can just kind of do a calculator here. Just put 3x squared minus 6x plus 2 in and kind of evaluate it. Take a value that's a little bit bigger than 1.58. You're going to find that that's positive. 3x squared minus 6x plus 2 is positive. When you multiply by 4, you're going to be positive as well. So the second derivative would be positive when x is greater than that second root you found at 1.58. At 0, 1.58 is one of the roots, so we know that the second derivative is 0 there. When x is between 0.425 and 1.58, a little bit of testing will show that 3x squared minus 6x plus 2 will be negative. 0.425, again, we said what? That we're going to have a second derivative equal to 0. And when x is less than negative 0.425, what do we know is going to happen? Again, testing just through the calculator, we would find out that the second derivative is positive. So wherever you see positive, concave up. Where you see negative, concave down. And what do you notice? What we suspected. When I get to a value of 0.425, I go from concave up to concave down. That's exactly what I'm seeing here. That looks like an x coordinate. That's 0.425. What do I also notice? My second inflection point, which I can sure see, is when x equals 1.58. Just like what I'm seeing on the graph, going from what? Concave down to concave up. And so the last piece of work is now take those two x values that I got where the concavity changes and figure out the exact coordinates. I need to figure out the y coordinate associated with these two red points. And how do I do that? I go back to my original equation. Y equals x to the fourth minus 4x cubed plus 4x squared minus 2. I'm going to evaluate f of 0.425. And when I do that, I get a value on the calculator right around negative 1.55. And when I make f equals 1.58, if I evaluate the function at 1.58, again, remember, what am I evaluating? Our original function. I'll come back with a value of about negative 1.56. Now, from a symmetry standpoint, the inflection point should have the exact same y coordinate. It's just because of some rounding in the calculator that I'm off by 1/100th here as I do some of my rounding work here. Don't be alarmed by that. Again, we're just kind of using the calculator as a tool here. So what's the bottom line in everything we've done here? We've used all the lessons of section 11.3. Analysis of the derivative, increasing, decreasing, moving from increasing to decreasing, or vice versa. We found critical points. We've identified, in this case, confirmed some relative mins and some relative maxes. We've been able to work with the second derivative to determine also what? Confirmation of max and mins using the second derivative test. And we've also done a nice detailed analysis of the second derivative through a sign chart to identify concave up and to identify concave down. And as we moved through concavity, we found a couple places where the second derivative was set equal to 0, and we noticed that our concavity changed. We were able to take those x coordinates where our concavity changed, run those into the original equation, in other words, evaluated the function where x is equal to those coordinates, or the value where we saw the inflection point come up. We were able to develop the y coordinate, and as a result, in our last piece of analysis, we were able to identify the exact coordinates of those two red dots. So go through this a few times. Don't hesitate, work it. Look through the homework problems that we set on 11.3. My answer keys are very, very detailed for these. I think you'll find them very valuable. Take advantage of them. Get yourself a solid understanding of 11.3 and you'll be in very good shape.